Hello folks, it is that time again, I'm afraid, where we are going to be delving back into the depths of the Jaguar I-Pace front motor inverter for another semi-fun filled reverse engineering session. Before doing so, I do have a little bit of knowledge that I would like to share. Thanks to a commenter on the last video in this series, we now know that this inverter is manufactured by a company called Vitesco Technologies and is listed on their website as the EPF 2.8 Plus. And from a little bit of searching around, seems to be quite popular with a few different OEMs. So, also on their website, they have another product that is, I believe, based on the same design, that they rather ironically call the open inverter. So, looks like we've some competition. I do wonder if it is open source though. So folks, with that out of the way, we are about to delve in. But final health warning before we do so. This is long, this is boring, it is not at all entertaining. So you have been warned, and I can strongly recommend funny cat videos as a viable alternative. But if you're still with us and you want to, you've got some, sleeping issues, you can't get to sleep easily, then stay tuned and let's get started on this thing. Okay, folks, we are back here having a little bit of a probe around on our Jaguar I-Pace front motor inverter. And we've made some good progress here. Just want to give you guys a quick little update on it. So, turns out the power supply for the gate driver is derived from the normal 12 volt line. There is a backup power supply there that looks like it works from the high voltage side. So it might be something that we need to look at for the high voltage measurement. Speaking of which here, see the way our logic board is removed, but I've just got it powered up here. I've got a scope probe on a pin here on the middle rear connector, because I was looking around to try and find myself a clock signal for that sigma delta converter, and sure enough, as you can see there on the well, hopefully you can see on the old bench view here, we've ourselves a spot on 10 megahertz signal here that is being kicked out on that pin. So I am guessing that that is our sigma delta clock, and that some of the other pins will contain our sigma delta bit stream. So, our delta sigma, or whichever it is, I can never remember which one. So what we're going to do is we're going to feed that with a clock signal, probably from the analog discovery, and we'll see what we can find. So stick with us. Okay, folks, we are clocking in here at a measly 1 megahertz on our analog discovery. And while it does say that it'll go to 10 meg, unfortunately, it has very little drive ability at that frequency, as you would expect, and can't really push the clock to the necessary levels that it would need to be correctly registered. But the good news is that with most of these things you can drop the clock frequency and that drops the data rate. So if we get ourselves organized here, we should be able to grab some scope action for you. And you're going to see here this rather wonderful looking waveform that basically is now disappearing. Yay, because I don't know what I'm doing. Alright, let's try that again. Okay, so this is basically an encoded kind of a data format. Oh God, I really am a screw up. Okay, this is, let's try that again. So, okay, I'm going to leave it. Brilliant. Okay, this is what we're getting back out of our Sigma Delta converter in there, which is just a serial bit stream. So it just goes high, low, and off to work it goes. And it basically just represents then the value that we're getting, which I'm going to assume, possibly incorrectly, is the high voltage bus voltage. Why they felt that they needed to, you know, use this kind of a method of getting that data, assuming that that is what we're looking at here, is a little bit weird. You know, I certainly wouldn't be doing that, but then again, that's me. So anyway, then again, I suppose if I had a tri-core processor and a lattice FPGA on there, I guess the sky's the limit. So anyway, right, so the good news is we seem to have figured out what we need here. There's a 3-volt enable line on there as well, very, very straightforward. And then it basically starts spitting this data out. It starts spitting this data out, and yeah, it's doing something. Yeah, it starts spitting. Oh, stop! It starts spitting the data out. Maybe this means I can click on it now. Oh, no, it doesn't. Oh, kind of does actually. Kind of does. Wow. Yeah. So, you can kind of see it a little bit better here, hopefully. So yeah, it starts spitting the data out. I'm not sure whether it's 8 or 16-bit. It's probably 16-bit. I'm going to try and figure that part out next. See if I can't screw up too badly. We'll try and get a capture of this as well and see if we can figure that out. But that being said, assuming this is the high voltage DC bus voltage, we will be able to just use a low pass analog filter to recover that. There's no need for anything too fancy, as we don't need to be too concerned about the accuracy of our high voltage DC bus. So, all right, I'm gonna kick off there. What else have I figured out? Oh yeah, the current sensors are plain vanilla. We just give a 5-volt power supply here on this center pin connector thing, and then it brings up all 3 of the current sensors. So I think the next thing that I'm probably going to have a go at is see if we can drive the IGBTs and get fault signals from them. So stick with us, or don't. Probably better if you don't. Alrighty, so we have made it way ourselves a little bit further along. So in here now we have some high voltage DC being applied to our high voltage DC bus. Now that is coming in from my cheap and cheerful power supply and is currently not reading anything. What is going on? Why do you do this to me? Why you do this to me? Why do you do this to me, multimeter? After all I've done for you. Getting you a nice license for your bench view and everything. There you go. So, we've got about 30 volts DC here on our high voltage bus. And that is consuming a whopping 128 milliamps according to my power supply. Now, interestingly, when we fire up this power supply here, which is our 12 volt derived power supply, the low side gate drivers wake up and apply about a negative 6.5 volts to our gates, which are here. So there we can see, yeah, about negative 6.3 volts on that guy. But now that we have our high voltage on, if we go to one of the high side gates, we'll see that we get, yeah, about our negative 6 volts there on our high side. And if I were to switch off my high voltage power supply, that pretty much goes away. And then I can switch on my high voltage power supply, and that wakes up and gives me negative 6.4 volts on my high side. But my low sides here are derived from the 12 volts, from what I can ascertain at this stage. So also our little sigma delta friend here does indeed seem to represent the high voltage DC bus. So if I put my multimeter on the data output line here, I should have a clock train going in there. Let me see if I can get my meter on that. You will see that what happens is the meter basically low pass filters that data stream. So if I increase the voltage now on my high voltage bus, you're going to see that voltage increase. So let's go up to about 40 volts. There's about 40 volts on our HV bus, and that's giving us 1.584, let's say, and go back down to 30 volts. There's about 30 volts, and we're at 1.563. So that is basically a low pass filtering of that data stream that we saw on the scope earlier. So this is pretty much telling us that this circuit here with the sigma delta converters and all this going on does indeed seem to be responsible for measuring the high voltage DC. So looks like what we've got going on here is pretty logical, in a sense that at least we can figure it out. We've our 12 volt derived power supply here that runs our low sides, our high voltage derived power supply here that runs the high sides. Now, interestingly, we have these little guys here, which are our ADUM 3211 drivers. Now, the supply on the, let's call it the logic side supply, seems to be derived by the 12 volt power supply. So let's see, we got 3.3 volts there. But on the high sides, let's see if I go on to this one now, we've got about 3.45 volts on this guy. And on the low side, try not to blow it up, 3.45. But if I turn off my high voltage here, then go back to these ADUM 3211s, we'll see this one has now got a dead high voltage side, but it does have a live isolated side, whereas the low side one has a live, does it have a live isolated side? Or am I just being an idiot as usual? Let's see if I can get in here a little bit better. It's so nice having, yeah, it does have a live isolated side. It's so nice having yeah, and that's so, yeah, so definitely the low side has got it's being derived fully from the 12 volt supply. If we kick our HV back on again, now we come back over to our HV side on this driver here, or this isolator. Yeah, we get 3.45. So, alrighty. Yeah, I was saying it's so nice to have a board that I can actually probe that's not covered in goo. But looking recently at some of Vitesco's social media stuff, they are going to cover their boards in goo. So, woohoo. Anyway, It shouldn't bother us too much as long as we can, as long as we know what pins do what. So, all right, so basically right now, our gate drivers are awake. All 6 of our transistors are turned off. We are clocking our sigma delta thing here just at 1 megahertz at the minute. Now we have verified that that is indeed reading the high voltage DC bus. So what I'm going to try and do now is we'll turn off all of our power, and we're just going to beep out between the 3211s and the headers and determine which. So there's basically one channel of this goes that way, one channel goes backwards. So what I want to do is I want to just make note of what does what. So before I do that, I'm going to turn off all of my power supplies. I have 1, 2, 3, 4 power supplies running here now to keep this thing in the habit to which it is became used to. So, oh, instrument is in remote mode. Oh, now great. I gotta try and figure out how to put my instrument into continuity mode here, live, obviously, so that I can be maximally embarrassed by my lack of. Well, we can do. This is great. We can do resistance. Can we do continuity? No. Range. Doesn't look like we can do continuity here. So, okay, so you're just going to have to... We're going to have to work with... okay, so it's aperture, auto zero, null state. I don't know what any of that crap means. So, okay, great. Let's continue with that. So right, let's see if we can figure out what pins on the ADOM do what. Or what pins on our header do what, I should say as well. So, let's see. Yes, okay, so pin 2 on the ADOM is the feedback. Pin 3 is the feed forward. So it's the feed forward that we want. So, okay, the feed forward. So this would presumably be the signal to the gate driver. So, want to take any educated guesses here, Damien? Not really. Okay, let's try this one. Nope, doesn't like that one. 10 kilo ohms. Not sure I like that. Could be though. Oh, there we go. 0.1 milliohms. I'm pretty sure that's our... yeah, I'm pretty sure that's a gate driver. Or a gate signal. Only am I just being a muppet again? Ah! There was me saying that I really enjoyed working with this board, but... Alright, there we go. So that one, that bottom in here, looks like that is our gate drive for that side. So let me a quick note out of that. Here, my trusty notepad. Okay. So if that's our gate drive, what is the bet that this pin here, beside him, is the feedback? Who wants to take a bet with me? Who wants to take a bet with me? Well, you'd have won, because that says 55k. Gah. Yeah, no, that's not very good, is it? Yeah, it's not that one. Not that one. Not that one. Not that one. Whoa, that's positively strange. Why would it be the same pin? That does not make any sense. Unless I have made a muppet out of myself again, have I? Okay, so that's definitely that one. Well, 0.2 of an ohm is pretty darn low. That wouldn't make a whole load of sense now, would it? Well, who cares? Let's just see what happens when we start driving it and see what it decides to do. But this definitely looks like this guy here. Let me just let me. Okay, give me a minute here. I'll try something. Alrighty, folks. So since our last section on this inverter, I'm pleased to say that we've got pretty much everything on our gate driver board worked out. So what I'm going to do is just give you a quick little tour through what some of the signals are doing, what some of the components are doing here. Before I do that though, there is one little gotcha that has been kind of the last thing that was catching me on this. So it turns out that, let me get my notes. Alright, so it turns out that the high side gate drivers they get their isolated power from the 12 volt derived power supply. So this transformer and this power supply section here, they get 12 volts DC in here, they get a ground, and they get a power supply enable signal, just a 3.3 volt logic line here, which is on this brown wire, and that turns on the power supply, brings up our high side gate drivers, and we see, as we saw there previously, about 6.5 volts negative on all of our gate emitters. Now when we then come along and apply some voltage to our HV, once we get up around 20 volts or so, this power supply here starts up. And this power supply is derived from the high voltage. And its job is to run the low side gate driver's isolated supply. So once this power supply comes up, we get a power supply good signal on this pin here, and that goes from 0 to 3.3 volts once the power supply starts up and tells us that we have a good power supply. So, and again, that happens at around 20 volts or so. So that's fine. We get our minus 6.5 volts then, as we saw on our low sides. But they will not respond to the control signal that we send to them. The high sides will. We can turn the high sides on and off, no problem. But that doesn't seem to make our low sides work. So I messed about, kind of seeing if there was some kind of an enable line or something going on here. And then I kind of started to look around this part of the circuit here. And there's two voltage regulators, and this guy in the middle got my attention, which is a dual comparator. It's an LM2903. And I started thinking, what are they doing in there with a comparator? And I started thinking, is there a minimum HV that we need here before it will release control of our high voltage power our low side gate drivers? So I'm going to spin you guys over this way a little bit. I don't know if this is going to work out. But over here I've got this kind of cheapy power supply. This goes up to about 60 volts. And that didn't make any difference. I then dug out this kind of just a cheap booster module. And this can put out up to 120 volts. Put that in there. And yeah, pretty much nothing going on. Still won't release the the low side drivers. So while I was messing about doing that, I then found another pin here that controls a, which one is it? Yeah, it's a DC bus. It's a high voltage DC bus discharge signal that basically puts a resistor across the high voltage bus to discharge away the high voltage that will be stored in the capacitor. Is a pretty standard feature in these inverters. So with that one there, if we leave it floating, it defaults to the resistor being on, so being connected across the HV. If we give it 3.3 volts, it turns it off. So that's fine. And so with 120 volts on here, still wasn't getting anything. So what I did, and I'm not going to show you this because it is really dodgy and I don't want to do it again. Obviously got my cars out in the driveway, so I basically made up a bodge lead, and I just tapped it straight into a 400 volt battery. Just brought that in here to the inverter through a 100 watt filament lamp, and got about, at the time, it was like 390 volts on the bus here, and lo and behold, the low side gate drivers start to work. So the minimum voltage is something that I don't know, but it is somewhere above 120 volts and probably below 360. I'm going to take a wild guess. It's going to be something like 240 or 250 volts, somewhere like that. I don't know. Obviously, and to be honest, yeah, I don't really know why they have gone to that bother. It's a little bit silly to allow you to control the high side drivers but not the low side drivers when you're below a certain voltage. I don't really see the point in that personally. Maybe there is, but anyway, with that out of the way, the good news is we've got full control of all of our gate drivers. As we saw there before, we have our current sensors, our 5 volt supply for the current sensors. They're just 2.5 volts centered. Current sensors, so that's ideal for us for the open inverter system. So over here, to say, we've got these chips. This one here is our Sigma Delta encoder guide that I was able to, as you saw there, verify that that is basically measuring the high voltage bus. Now, this guy here beside him, I thought was working with him, but they're in fact two separate entities. This part here is basically a, this is a kind of an isolation amplifier. It is a AMC 1301. And what it's doing is it can measure an analog signal on one side, isolate that, and then pop it out the far side as a differential voltage that you would read into, either using two analog to digital converters on your micro, or you can convert them into a single-ended signal with just a little op amp. So I'm assuming, because I don't know yet, but I'm assuming that this guy is our heatsink temperature sensor. And it might even be that the reason that they've done it like this with this isolation amplifier is down to the fact that they may be using a temperature sensor that's built into the IGBT package, and thus isolating that from our control logic would be, I guess, a good idea. Not 100% sure about that, so I am going to do a little bit more investigation, because even as I'm talking about that now, that does seem just a little bit weird. There's also two optocouplers here. They're back to back. So this guy here is going into the board. This one's going out of the board. Was able to determine that one of these pins here is a power supply for the isolated side of the one coming out of the board. But what they're actually transmitting and what they're actually doing, I do not know, because their signal pins, either on the one going in or the one coming out, do not seem to be brought out to any of our headers. So they may be doing some internal wizardry that I don't know about. It could be something to do with this minimum voltage detection, or even to do with the discharge control. So I'm not sure. I'm not sure what's going on there. But other than that, we've pretty much got everything that we need to make this thing work. So I'm going to poke around a little bit more just around this part of the world here to see if I just want to convince myself that I'm right, that the big sigma delta converter chip is doing the high voltage bus measurement, and that this guy here is doing temperature or something like that. So I do have to have a look at that just to be sure. Fairly certain on the sigma delta, but I am just going to verify this guy here. So all right, I'm going to do a little bit more work, and we should be able to wrap this up fairly soon then. And at that point, we can start to design ourselves a replacement for this thing that will actually let us run this inverter without all of the associated flex ray and communications with God only knows what else that it would want to have. So, all right, on to the next part. Okay, so this is where things just get a smidgen weird. Right now we're connected with our multimeter across basically what's called V out P and V out N from this isolation amplifier here. And you will see that we're reading about 116 millivolts. I've got exactly 30 volts on our DC bus here. So I'm going to go ahead and slowly increase this now. We're coming up, and there's about 35 volts. There's 40 volts. And there's about 50 volts. There's a little over 60 volts. So there we seem to be measuring our high voltage DC bus here by means of that isolation amplifier, as well as with the sigma delta. So anyone want to explain that one to me? Because I doubt that, I mean, if this was measuring something else on the board here, you wouldn't want it to change as much as we can see there. You know, if I go back down to 30 volts here, all right, so there's 30 volts. So yeah, we certainly wouldn't want something to be changing that much without it being actually measuring the value. So that's strange. So what I'm going to do now is I'll rig the analog discovery back up. We'll get it clocking again, and we'll see if we can we'll see if I have made some kind of mistake here. Is the sigma delta measuring something else? Like I said, I really can't see how we can get that much of a voltage change on something without it being measuring the thing. I mean, if I turn off the power supply, what happens? Okay. pretty much goes to, I guess, a zero value, because there's nothing happening on that side. Crack it back on again, and there we go, back to 116 millivolts. So yeah, that one is definitely strange. So if we dial this, let's dial this back down. There's 25 volts coming down. There's 20 volts now. So I mean, that really has to be representative of the DC bus. So right, okay, let's rig up again to the Sigma Delta Sigma, or whatever it's supposed to be, and see if we can make some sense out of this thing. Okay, so this is where we're getting to here. I've been messing about with this Delta Sigma thing. I've got it clocking now. I've got a clock frequency of 5 megahertz going in here. We're taking that clock from our Keysight scope, which can generate a 5 megahertz TTL clock. And we've been just looking at the data waveform here, just looking at the RMS value of it, really just trying to figure out what's going on. Now, I'm not really getting much useful data from that. So what we'll do here is we'll go back to our, we've got our multimeter here again. So what I'm going to do is I'm just going to hot swap the multimeter between the two. So what we've got now is I've got about a little over, let's go to 20 volts exactly on our, that's close enough to 20 volts on our HV bus. And that's giving us about 78 millivolts now, coming back out of this differential isolation amp. So 78. So if I go up to 40 volts, we should see something under 160 if it's ratiometric. So there's about 40 volts, and yeah, that's close enough, particularly down at that kind of a low level. So okay, so let's go back down to 20 volts. Here, yeah, there we go, it's about 20 volts. So what I'm going to do now is I'm going to move my multimeter off the differential amplifier and move it. We've got to prat around a bit with this because I've got scope probes and all kinds of things going on here, and connect that to our output of our Sigma Delta. So 1.74 volts, 1.747 at 20 volts. So let's go up to 40 volts. There's 40. 1.798. I mean, it's definitely tracking it. Let's go up to 60. There's 62 volts. We've got 1.854. Now the thing that we have to be conscious of is that, you know, this is just a multimeter averaging that high frequency bit stream. We can obviously do a similar thing, but for all intents, folks, I mean, at let's say the 1.854 there, so let's go all the way back down to 20. Sorry I can't show you the things in parallel. I don't have enough Keysight instruments. So there's, again, about 20 volts, and we're back to 1.747. So it does seem to follow ooh, don't short circuit on me. Don't short circuit on me. Come here. Silly, I've got way too many wires here. Anyway, so let's go back onto our differential amp. And yeah, there's, 78 millivolts. So it does seem that there's two ways of measuring the high voltage bus. We can have a differential analog, or we can have delta sigma. Don't know what that's about, but that's what I've got for all intents and purposes. I yet haven't been able to find any kind of a temperature sensor in here, which would make sense. I mean, I can't see how the differential amplifier that you're looking at on the screen there now can be a temperature sensor when it varies so much with the HV, nor can I see how the delta sigma could be a temperature sensor. I think that would be definite overkill. So yeah, it looks as if we're going to have to see if there's any pins here that I don't understand. There is one pin here on the gate. This top pin here, I haven't quite figured that pin out. So I wonder, is that pin something to do with, is that pin or this pin? Okay, so there's actually two pins on this connector that I don't know. I know all the pins on this one, all the pins on this one. There's two I don't know on this one. I know all the pins on this one now, with all the double methods of measuring voltage on them. And I know, okay, there's one pin here that I don't know. So, okay, so I have one pin here and I got two pins here. So I'm going to go away and see what's on those pins and see if it somehow correlates to some sort of a heatsink temperature sensor. Maybe. Maybe they don't care about the heatsink temperature, but I would find that a little bit strange. Okay, let's go probe around some of these unknown pins here. On this gate drive header here, I've got this pin here, which has got nothing. And next one down then is just two down from him, which also, okay, hang up. That's interesting. Was that some kind of or that did something? It looks to me like a short circuit nearly. Yeah, maybe. Sorry, it's this pin. I was going on the wrong pin. Of course I was. Okay, no, there's nothing happening on that pin either. There's nothing that would even remotely indicate that there's a signal or anything that might represent a temperature sensor. So on that note, there is one pin over here on this guy that I don't know anything about. So let's see if he has anything interesting to tell me. Yeah, this guy here, this last one on the bottom. Okay, 5 volts. Interesting. Is that just a 5 volts output, or what is it? I don't know. I'm gonna say, yeah, I'm gonna say that's probably not a temperature sensor. It'd be a bit weird if it was. It could be. Yeah, it could be. Let's leave that as a possibility. So, okay. I think what I'm going to do now is I want to have a look at these two devices again and just see, because this is where on these little pins here, I did manage to discover. Where is it gone? No, not that one. This one. If we look at that 79 millivolts, okay, that is coming off two pins that are coming up from the from the IGBT pack. And that is 79 millivolts there now. And if I can, my other hand over here to the power supply, as we increase our power supply voltage, look at what happens. So that increases. So these two pins here are being passed through the isolation amplifier here. So they then come out of the other side of the isolation amplifier as a differential signal. If we look, where's it gone again? So it's 116 millivolts on this side, on the non-isolated side. If we grab our wires here now, I'll just my finger on them. Close enough to 116 millivolts for me. So definitely our isolation amp is reading high voltage via some kind of mechanism in the IGBT pack. Okay, so let me just have a little probe around on our delta sigma here, or sigma delta, I can never remember which. Of course, I could just look up the data sheet for it and not be a muppet. 21 millivolts, 5 volts. I'm going to have a look up the data sheet for that delta sigma. Be sure I have it handy here. Let's see, yeah, here it goes. So, okay, so pin 2 and pin 3, analog in negative on pin 3, analog in positive on pin 2. So basically, between pin 2 and pin 3, we should have our, whatever it is, 116 millivolts if this thing is reading what we think it is. So let's see if we can get in here on pin 2 and pin 3 of this thing. Mind ahead. Oh, I do see, interesting, there's two little filters, little filter components, probably little inductors. Alright, what do we got? Well, that is 13 millivolts. That is not previous one. Now that could be scaled in order to suit the, that could be scaled, in fact it probably is scaled in order to suit the sigma delta. So let's see, I don't know how I'm going to be able to do this because I really do need 3 hands here, but alright, at 30 volts I'm going up. There you go. So there's 40 volts at 18 millivolts, 51 volts, 24 millivolts, back it up to 62 volts at 28 millivolts, and back down. So our delta sigma, there's, let's go down to 20 volts. There's 20 volts, yeah, 10 millivolts on there. So our delta sigma is indeed measuring the high voltage bus and this isolation amp. So that's weird. I don't see why you'd want 2 methods of doing it, but maybe this power stage is used with different logic boards. I don't know. Anyway, that solves that little mystery. It still doesn't give us a temperature sensor, which is kind of the last piece of the puzzle. It's possible they do their temperature sensing elsewhere. I wouldn't think so. The only as I said, two things that I haven't been able to work out are these bidirectional, these optols that are working in the opposite direction. So I'm going to go have a play with those optols and see what life brings to us. Okay folks, I think we have it. We've found our heatsink temperature sensor. Let's give it a little bit more heat. I have been warming the base of the inverter here just with the old Milwaukee heat gun. And it's starting to pick up speed here at a rate of knots. This originally started out, when I found this yesterday, it seemed to be sitting at around 5k, and it seemed to be affected by heat, but I couldn't really be sure. And I think that was because the heater that I have under the bench here to keep my toes warm had obviously thermally soaked the thing, so when I was heating it with the heat gun, it didn't really make that much of a difference because of the large thermal mass of the inverter. But when I came out to the workshop this morning, it was colder, obviously after last night, and at about 8.5k on there, and I noticed it was slowly dropping because I'd turned the heating on. So then I just started hitting it with the heat gun, and as you can see there now, it is it's really starting to pick up speed. It is heading down rather rapidly. It's located here on this first IGBT driving connector, and it was two pins that looked to be connected to nothing. They weren't connected anywhere like to ground or supply or anything. When I measured between them, I found this resistance, and as we can see here now, it does indeed seem to be temperature affected. It's really starting to pick up speed now. So yeah, I think it's safe to say, that's warming up more rapidly now. So I think it's safe to say we have ourselves some kind of a resistance temperature device here. So that's it, folks. That is our last kind of signal that we needed to find for this thing. So there's really nothing to do now but to go off and design ourselves a logic board to replace this one, and get that front motor running with some open inverter action. So, yay, heatsink temperature sensor. Alright folks, so just to wrap things up here on the temperature sensor, I ran the data logging thing here on BenchView with the multimeter for just under 2 hours, and I various points here turned the heating off and turned the heating back on and turned the heating off in the shed, and you can kind of see that it was indeed kind of following that track. So I'm pretty confident that we have ourselves the heatsink temperature sensor there. What I'm going to do is that multimeter that I have can actually log from, I think, either thermocouples or RTDs or stuff like that. So I'm going to get something that we can graph it against and do a few tests that way, so we can get a few data points and hopefully be able to program this thing into our open inverter. But yeah, that's it. It looks like we finally got the last signal that we needed here. Okay folks, a little bit of, I guess what you might call bonus content here. I got myself one of these little simple kind of kiddies USB microscopes, just so we could see how it would work with kind of looking in at some of the fine pitch surface mount stuff that we're dealing with here. And much to my surprise, it seems to work rather well. So I thought we'd just have a little bit of a look at the logic board here just for a few minutes, just more so just to, I guess, see how this microscope thing works. So we're looking here, let me get a little pointer. We're looking here just at the CAN controller. This is a CAN transceiver, I should say. It's TJA 1043. So going immediately over from that, it's this little guy here, which if memory serves is our FlexRay transceiver. I can't really see the writing on that too well, I suppose, but I could kind of focus the camera a bit if I needed to. But so coming back up to the top part of the board, we've this guy here, which is our 50-way FPC connector. So I've ordered, I couldn't find the exact one on any of the suppliers' websites, but I've ordered one that is, you know, pin and pitch compatible. So with a bit of luck, this guy will, you know, we'll be able to connect the original ribbon cable on here and just yeah, be able to just use the original external connector then. What else is interesting on this board? Well, let's go over here. This chip here, I haven't been able to identify. Again, no big deal, I suppose, but looks to be some kind of a power supply chip. It's in a 64-pin QFP. What else? We've got a couple of transistors there that are just used for switching 12-volt power, I believe. I believe these two here are used for switching 12-volt power on and off to the gate driver board. What else is going on here? Probably not a whole lot else interesting. We can just about begin to see our famous Infineon tri-core processor there. This is the camera at the kind of top of the little stand that I've got, so it's kind of zoomed out, so we can zoom in a hell of a lot more, but you can clearly see, like, it's pretty good. You can see all the pins there. We could certainly zoom in more on it. Let me flip the board around. What else? So obviously these are our connectors here. This is kind of the middle phase connector here, and you'll see the way there's a kind of a heavy track going to this pin, and that pin is our 5-volt supply to our current sensors. And then we've our gate drive and our fault signals here, and there's this little bit of logic goes on here with this little 5-pin. Where's he gone? This little 5-pin packaged part is on all of them. So I think it's some kind of a little buffer, or it could even be an inverter or something. I guess it could be both. It could be an inverting buffer or something like that. 10K, either a pull up or a pull down. I didn't really bother to figure out which. There's a little filter cap on that 5-volt line going up there. If we come down to, I guess you call it the A phase, you'll see there's another little bunch of logic here. This is repeated on all of the gate connections. And we come down here. All the little bits of crap on my bench here. Don't like to let the thing move. And then there's that little buffer chip again. Going on there. And if we just go up to the, I guess we can complete it. You can go up here and see again on the, I guess the phase C, you've got this little bit of logic going on here. This little, I'm calling it a buffer chip, and we just connect there. So that's our fault. No, sorry, is it? Can't remember off the top of my head. I think that's the fault signal. No, that's the driver. That's the fault signal. And up the top then you have a similar situation. Some devices here, not quite sure what these guys do. There's an ST part. Recognize that part. Is it an ST part, or am I just going nuts? Yeah, yes it is. Yeah, there's two ST parts there. And some, I guess these are transistors. BCP 53s. I'm guessing there's some kind of driver. Transistors maybe for optional contactor control, or that wouldn't be contactor control, would it? Hard to know. And here then, if we continue over this way, there it is. Look at that. The Altera Cyclone 4, is it? Yeah, Cyclone 4. Nice BGA, FPGA there to keep us on our toes. So yeah, that's it, folks. Just a quick little tour of this logic board that we're going to be replacing. Yeah, so I do like the little cyclone symbol. Never messed with Altera FPGAs. I've done a little bit on the Xilinx Spartan 6 for the Tesla Model 3 BMS, so I guess there's just so much stuff to learn. It's crazy. So just what else is there? Just some passives around our Infineon friend. Look at him. Get that Infineon tri-core. 3 cores in there. Well, I guess 3 cores are possibly better than 1, but we'll be replacing this lofty device with a simple STM32F1. Stick with us. Well, folks, I do hope that you have enjoyed this little segment. It was a bit of a struggle finding a few of the things, but not anywhere near like it is with the Tesla stuff, because at least with this design, they're not trying to deliberately obfuscate what's going on, at least that I could tell. So as you saw there, we had a couple of strange findings. I guess the dual method of measuring the DC bus voltage, whether you like analog or digital, seems you can have your pick. We'll be going for the analog method on our logic board, because that means we don't need to worry about clocking the sigma delta converter. We have, as you saw there towards the end, finally found the heatsink temperature sensor, and I'll be doing some data logging with the multimeter and Keysight bench view there, just to prove that when the workshop warms up, the temperature drops. When when the workshop warms up, the resistance drops. When the workshop goes colder, the resistance increases. So pretty sure that is in fact our final signal. Other little weird thing I suppose that we have there is the way they drive the PWM signals, that the high side you need to drive them high to turn them on, but the low side need to be driven low to turn them on. So we'd have a little bit of a couple of little inverter or something in there to run our low side. So I think that is about it for this episode. Do hope you have enjoyed. It's been a bit of a challenge, but you know, that's what we like here. So I'm going to go ahead and design a board based on the open inverter system that we'll be able to then drop into this guy here. Final thing we'll want to do will be just sorting out this 50-way FPC cable here, just to get the pin out for it to match up to the external connector, but that's literally just continuity beeping, so I'm not going to subject you to that. And of course, as always, these designs will be published on GitHub, completely open source. And hopefully, once we get the bugs out, we'll be selling these in the EV BMW web shop for all of you iPace and or other Vitesco based inverters that you may wish to use it for. So that's it, folks. I'll leave you there. As always, do not forget to dislike, unshare, do not subscribe to this silly channel. And whatever you do, don't support me with Patreon or PayPal or any of that stuff, because then I'm just going to do more of this thing, and that's bad. So other than that, there will be links in the description for GitHub and the Open Inverter forum and things like that, where you can join in the fun. And yeah. So until next time, happy temperature sensor logging.